So let me try again. Just let me know whether that is now any better. So I've switched off the other computer in the office just in case it's causing the interference. It's better. That's super. That's super. So we'll wait for, we're still waiting for another 20 people who are probably trying to rejoin. Or they had gone for a cup of tea and they don't know what's happened. So. So I think we carry on. We might have lost 20 or so people, but yeah, it can happen. Please convince yourself about these numbers, about the size of the chip, a flash ADC versus if we do the conversion within 2 steps. This particular building block, we'll probably look at the detail of it before we complete the course. It's called a sample and hold. Remember, each time we've sampled, we've kept the voltage. It's a varying voltage, but once we sample, we keep that amplitude. So the circuit that does that is called a sample and hold. And we particularly need it when we do this type of ADC, because this input voltage, we need to use it to be able to create, to determine the difference between the representation from the first 4 bits and the actual input voltage. That difference we use to determine the final 4 bits. So we need to, once we've sampled the signal, we need to hold it until the conversion is complete. So until we have all the 8 bits. And so we need a sample and hold circuit at that point. And yeah, the reason for doing this, yeah, the 2-step ADC is a faster version. It's a slower version of the flash ADC. And we make that compromise because of it will be cheaper, runs relatively fast, but it's cheaper. So for some applications, the 2-step or sub-branching ADC would be an interesting variation. Using this idea, remember our input voltage Vin. If we return the example of we want to represent Vin with 8 bits, so that's B1/2, B2/2 squared, up to B8/2 to the power 8. So in what we just looked at in the first 20 or so minutes was we split, we determined the first 4 bits, and then we the remainder of the bits we determine them after using our first digital equivalent and the sampled input. So instead of doing that, we could determine 1 bit at a time. And how do we do that? We know in this particular case, if we're looking to represent our input voltage with the 8 bits, so Vin to be equivalent to that. So approximate Vin with the 8 bits. To determine this 1 bit at a time, it means that Vin initially will be equal to Vref into B1/2 plus V error. Just using the same derivation as we've just done. Here, V error will be equal to Vref into B (2/2 squared) plus B3/2 cubed. So we have an input voltage. We want to represent it with 8 bits, but first of all, we represent it just with the most significant bit. I have the message that my connection is unstable. I think, yeah, we hang in there. I'll try to speak slower and give time for questions where the they go through this slowly and systematically. So we have our sampled input voltage. We want to represent it with 8 bits. First of all, we represent V in just with the 1 bit. So if we do that, it means that the remainder, the error voltage, will represent the remaining bits. So the error voltage, we could represent it like that. And so actually this error voltage, V error, will be equal to our input voltage, V in, minus Vref B1/2. It will be equal to that, and that will be equal to this. And this one, we can factor out the 2 so that the remainder of this expression is similar to what we would expect with an ADC. So it will be B. Of course, if this 2 goes inside, then it's equivalent to the error voltage. What this tells us is that if we sample yeah, I got a message that the link is unstable. The video, let me see if I can. Yeah, I can. It's not out of focus. That's the best picture I can get just now for the video. But not today. Okay, this one, we have our input voltage and we put it in a sample and hold. The reason for that is as in the previous example that we did, and we go to a 1 bit flash ADC, and the output of this will be B1, and this B1 we go to a 1 bit DSC, and what we have here is our approximated input voltage, and this is our input voltage, and we subtract it from that, and at this point we have V error, and the error voltage there is the other 7 bits. For us to do this, we need to amplify this by a factor of 2, Once we've amplified it by a factor of 2, then we have this expression here. And this expression here is of a regular ADC. The most significant bit, it's weighted by half. The next most significant bit is weighted by a quarter. So we could determine this also by a 1-bit ADC. So at this point, this output here and input it into a sample, we hold it steady, and then we could put it through a similar process. If we put it through a similar process, we'll be able to determine B2. And once we've determined B2, we can also put it through a similar process. So at this point, I would go into a sample and hold. And out of this, I would determine B2. Once I've determined B2, I'll have an error voltage. I do exactly the same like this, and I'll be able to determine B3. And I repeat the same procedure, so we can repeat for B2, B3, B4 up to. So some detail about this. It's 1-bit flash ADC. If we are determining 1 bit with a flash ADC, this one, it will require it will just be a comparator. Remember, flash ADC for 1 bit, you'll have your VREF, and you'll need 2 resistors, and this is 0.5 R. This will be 1.5 R, and this will be an input voltage, and this comes into your comparator. And then you have your clock input there. Actually, for this, we don't even need the, and we have B out there. Decoder not required. Search encoder ADC. So just the comparator will be able to do the job. So just looking at that, we have our input voltage. The input voltage, you want to represent it with 8 bits. So that voltage, we determine the first bit with 1 bit flash ADC, which converted back to an analog equivalent. We subtract that from our sampled input, and the error voltage will correspond to the 7 remaining bits. From the simple algebra here, we know that we need to amplify the error voltage by 2. Once we've amplified it by 2, we have the signal that we have, we can convert it with a 7-bit flash ADC if we needed. But we don't need to do that. We can just determine the most significant bit, which will be B2. And a 1-bit flash ADC will also be able to do that. So we'll determine B2. And because we need just like the input voltage, we not only need it here for the 1-bit flash ADC, but we need to use it here to generate the error for the next part. So we need to hold it, determine B2, generate the error, and so on and so forth. And for that reason, this is called a pipeline, or a pipelined ADC. S and H is mandatory. For you to be able to do this, S and H is mandatory. Do we need to, one question that we need to answer is, do we need to wait until all bits are determined to take the next sample? So an important question about this architecture is the so-called pipeline architecture, is whether we need Marwan, I'll come to your question in a second. Let's answer my question first. Or probably we need to understand, I need to answer yours first before we answer this. But yeah, I'll come back to that in a minute. I'll just use the handout to show this again. So the handout, that's a picture of the pipelined ADC architecture. So we sample and hold actual K with the pipeline architecture. K would usually be equal to 1. So 1-bit ADC, which is just a comparator. 1-bit DSC, you want to tell me what nature that takes? Then we have an amplifier, K is equal to 1, so that's just twice amplification. Yeah, but for each bit, we need this, and each bit can be done in just under, so 1 clock for that, and you can take 1 clock for the rest of the signal to reach there. So actually, from the picture above, you probably see that actually during the first phase of the clock, we can determine the first bit. During the second phase of the clock, the error signal and amplification can be done. So actually in 1 clock, we can determine 1 bit. So out of the 8 bits, so for the 8 bits, we determine bit 1, then bit 2, then bit 3, bit 4, bit 5, and bit 6. So I'll probably answer the question about the reference voltage before we go back to my question. So when we do the conversion here, we use the same reference voltage. And that's because, I'll just take that away. This is where we started. We sample an input. We want to represent it with the 8 bits. So the reference voltage that we use to determine B1 is the same as we used to determine B2 up to B8. If we didn't use the same reference voltage, then of course the contributions will be different. So for B1, the reference voltage is what it is. And by providing this amplification of 2, it means that we can use the same reference voltage to determine those values. They're a bit smaller, but this amplification means that when we determine B2, even though B2 is a quarter, but because we bring in this amplification, it brings it to the same level such that B2 will correspond to a quarter with the original reference voltage. Hopefully that clarifies your question, Marwan. So having done that, then for this architecture, just a minute. Is we have 8 bits, we determine B1, then B2, then B3, then B4. And our analog signal is something that varies in time like that. So we take the sample, then we determine B1, B2, B3, B4, B5, B6, and B7. We could wait until we've taken all the bits before we take the next sample. Then we determine B1, B3, B1 to B8, and then the next sample. The question is, do we need to wait until all the 8 bits are determined to take the next sample? Could I get at least 2 answers from the class to that question? Ideally, 1 BN student and 1 MN student. One BN and 1 MSc student. Many of you are blocks on this course and you probably enjoy. So I have one question. Maran thinks yes, we have to. So we have yes and no. So I have 1 vote for that. Someone else? I have 2 votes for that. One more BN student and 1 more MSc student respond to that question before I give you my view. Yeah, but before I give you the answer, I was going to say I listen to football, mainly on radio. Okay. Occasional on TV. And many of you might have thought if it's on radio, you get it. A goal before it actually comes on TV. If you've experienced that, it's the reason for that is because of this question that I'm posing. So 3 people think we have to wait. One more person, please, before we. Actually, the correct answer is we don't have to wait. So if we don't have to wait, what must we do? So we determine bit 1. Then the signal propagates forward. We determine bit 2. If the answer is no, that means once we start determining bit 2, we can take a new sample to start determining bit 1. Yeah, and Maran, you are right. So for sample 1, we determine B1, B2 to B8. We store them somewhere. So once we determine bit 1, we don't need to wait until we've done all of them. So we store them somewhere. Then we start, as soon as bit 1 is done, we go to the second sample. So this is sample 1. We go to S2. And for sample 2, we'll also have B1, B2 to B8. Because it's digital, we have storage facilities. We can track the bits for each sample and store them. And when we recreate, we know that those 8 bits correspond to sample 1. The next 8 bits correspond to sample 2. The next 8 correspond to sample 3. And so when we reconstruct the signal, we know which bits to use. And because of that, speed, we can say that the speed of this ADC, it's fairly fast. Yeah, but of course you have to buffer, and that's why I gave the example of if you don't listen to live spot, this example probably it doesn't make sense to you. But the signals where we need this kind of buffering, the TV signal would normally be a bit later, and the reason for that is you're using this kind of ADCs and the signal is being stored, so it takes a bit of time to be able to recreate it. And while on the radio, the signal is probably coming direct, and so it's a bit quicker. And that's with the first 3 main parts of the course. So the basics of analog VLSI, digital to analog converters, you should be familiar with them. In terms of the ADCs that we've done, they're all called Nyquist. Some textbooks will use this title. Nyquist, with relationship to the bandwidth of your baseband signal, it's the sampling rate is twice the highest frequency component that you're sampling, and because of that, both the DACs and the ADCs that we've looked at, they're called Nyquist rate ADCs. From Wednesday, we start on the first major topic of the course, which is called oversampling ADCs. Which sample at a much higher rate than Nyquist rate ADCs, but we start with a specialist topic called switched capacitor circuits because they are important in the realization of the other type of ADCs. I think apologies for the internet on behalf of the university. Normally it works, but we'll see you on Wednesday unless there is a final query via the chat. Yes, Marwan. Yeah, so we store it somewhere. That's why it's called pipeline, so that we when we'll have a tutorial. So probably the next week on Wednesday. So not this week, not on Monday, but next week on Wednesday we'll have a tutorial. So I'll email the class to confirm the same. But next week on Wednesday we'll have a tutorial to there's a tutorial sheet on the handout, and I'll try and put together a few questions and a few questions in the exercises, and also any bits of the class that have been unclear. So next week on Wednesday, but next week, this Wednesday and next Monday, we'll have regular lectures. We'll start with the oversampling ADCs. Okay, take care, guys, and see you on Wednesday.